I'm so excited. Somebody took me up on my offer to make extra videos by request. So for those of you that have been struggling and haven't requested a video, be thankful that this person spoke up, because now, hopefully, a couple of examples I'll show you here may help. The particular topic of interest is the topic 12, I believe, which is probably one of the roughest topics in this entire semester of Calc 3, and that's figuring out what the heck is going on with limits of triple integrals in coordinate systems that aren't rectangular. So instead of going right for that and being presented with a problem and having to design the limits from scratch, what I'm going to do is give you some examples here of triple integrals that are already formed and backing out the geometry that they represent, because maybe that will help in the reverse direction as well. So these first two are in a coordinate system that is not rectangular, and even without me telling you what it is, you should be able to recognize it as cylindrical coordinates, because we have r, theta, and z as the primary variables, as opposed to x, y, and z, or rho, theta, and phi, right? So what's going on? What is this particular integral right here calculating? Well, let's break it down. First, remember that in cylindrical or spherical coordinates, the dv, which is the current upgrade of the dx from Calc 1, has to be unpacked. And in cylindrical coordinates, the dv that trails the integral is r dz dr d theta. And so this business right here is actually r sine theta r dz dr d theta if I borrow one of the r's from the r squared. And so this is r sine theta dv. And what that means is, if we flip that back to rectangular coordinates for a second, isn't this y? So we're basically integrating y everywhere within a three-dimensional region. So we're not calculating a volume, we're just accumulating values of the function y over a region, which apparently is best to describe in cylindrical coordinates. So let's unpack the coordinates. I'm going to work from the outside in. Theta is on the outside, and remember, theta is the radial coordinate. So in a three-dimensional coordinate system here, theta tells us how far around we're going in the counterclockwise direction down in the xy plane to trace out the region of interest. It's the same theta that appears in polar coordinates. The limits on theta for this particular integral are 0 to pi over 2. And so that means that we start here at theta equals 0, which is pointing down the x-axis, and we're going to carry over until we get to what we would think of as the y-axis, but no more. So we have sort of a quarter circle traced out in the radial direction. R in the middle is going from 0 to 2. And so that means that, well, let's say this was 1 and then here was 2. That means we're actually filling in, at least in the xy plane, all the way out to there, to a circular boundary 2 units away from the origin. And then z is going from 0 to 4. So our region of interest is starting down here in the xy plane and heading up to z equals 4. So basically what we're looking at is a 4-story slice of pizza in this particular case. So kind of like this. So at z equals 4, we would still sweep out a quarter of a circle. Theta 0 goes from 0 to pi over 2. And 2 units out from the origin, r goes from 0 to 2. And then we have this kind of standing column in the first octant. So it looks like we cut a piece of pizza that was a fourth of our plane, 2 units out, and then it got stacked up until we got 4 stories tall. So again, it's a 4-story tall building in the shape of a pizza. And we are going into this weirdo 4-story pizza pie, and accumulating values of the function y, which is also known as r sine theta in cylindrical coordinates. So again, not calculating a volume, just doing three-dimensional accumulation of a function, which is what we can do with triple integrals. All right, this one's it's a little bit more complicated, but only because the limits on z are not constant values like they were above. Okay, but let's just think about r and theta for a second. Package those two things together. The limits here are demonstrating theta going from 0 to 2 pi and r going from 0 to 1, which means that down there in the horizontal plane, here's r equals 1, we are sweeping out to find our region an entire circle. So theta is going all the way around 0 to 2 pi, and we're going out a distance of 1. So in the xy plane, we have the unit circle. Now, what's going on in the vertical direction, in the z direction? Well, our lower bound is z equals r, which is also known as, by the conversion formulas, the square root of x squared plus y squared. This is a cone, and in fact, it's the cone that's on a perfect diagonal. The upper limit of integration is z equals 2 minus r squared, which, to put in more familiar territory, using the conversion formula r squared is x squared plus y squared, that's a paraboloid. And in fact, it's upside down because it's 2 minus x squared plus y squared. And so what this means is that our region of interest is hovering over the unit circle. The basement of this region is the most perfect diagonal cone. So let me see if I can draw that cone. So here's that cone. This is z equals r. That's supposed to be in green. That's the basement of our region of interest. And then here's z equals 2. Z equals 2 minus r squared is that upside down paraboloid. And again, we're going all the way around because theta goes from 0 to 2 pi. And so if I pick one last color, this diagram is already cluttered, but I'm going to do my best. We're going in a three-dimensional region whose floor is this cone and whose ceiling is this paraboloid, and we're going out to the edge of the unit circle all the way around. Like that. So it almost looks like a hamburger with a pointy base. Three-dimensional math always goes back to food, right? Now, the interesting thing about this is that the 0 and 1, I don't believe actually represent that point of intersection. So here we just go out to a distance of 1 and then stop. And so these sides of that region might actually be straight up and down instead of actually coming to that point of intersection. You could find where that point of intersection is by solving for intersections the way you always do. By the way, this integral, because we are integrating the function 1 times dv, that means we are calculating a volume. So this particular triple integral is finding the volume inside this region, which has a cone as the floor and the paraboloid as the ceiling. Now we're going to go the other direction and take a region that's being described in rectangular coordinates and set up the limits that would be involved in a triple integral that used this region. We won't evaluate the integral because we don't know what we're integrating in this problem. We're just practicing with limits. If I hadn't just shown you a bunch of stuff about cylindrical coordinates, you ought to be able to tell that this particular region would be best described in cylindrical coordinates. Hopefully by now you recognize that when you're dealing with a region with a circular cross-section, using rectangular coordinates is no fun because then your bounds are going to be things like the square root of 4 minus x squared, and that's horrible. So the edges of a circular region like this in cylindrical coordinates are tidy. And then here, this upper bound on z equals 3 minus x, you could recognize that as a plane, and planes are no good in spherical coordinates. So we have circular aspects to this geometry, but we also have a plane. So we'd like to leave z alone and just let z be z, and then use r and theta to describe the cross-section. So we got cylindrical coordinates. So what are our limits going to look like? to set up a couple of things here. Boy, that's a really bendy y-axis there, but we'll leave it. So I've got some axes weighting, and I've got the template for the triple integral weighting. This dv is going to be r dz dr d theta. All right, so in the x and y direction, we're in between 0 and x squared plus y squared equals 4, which means in the xy plane, we're looking at a circle of radius 2 as the outer edge. However, we have that extra restriction that y needs to stay positive, and that means that in the xy plane, we're only looking on that portion of the y-axis. The corresponding points there are in the upper half plane. Looks like somebody wearing headphones. And so, if we, as usual, have dv as dz dr d theta, then the integrals from the inside out are z r theta. We don't want theta to go all the way around from 0 to 2 pi. We want theta to go from 0 to pi over 2 to pi. And for any particular value of theta that we're going to use, any of those, r is going to go from 0 to 2. And so now let's take that over to the full picture here. There's the basement of this region. In the z direction, we're going to go from z equals 0 up to z equals 3 minus x. When x is 0, that's up here at z equals 3. So this plane is going to go through that point, and it's going to slant like that, right? So here's the roof of that particular solid, which is just, I'm just drawing a line to represent the plane's cross-section with the paper. And what we can see is that for any starting point in this region, in the vertical direction, we're just going to go from 0 up to the plane, 0 up to the plane, from 0 up to the plane. And so the z limits represent a region going from 0 up to the plane. Now the plane wants to be 3 minus x, but we are in cylindrical coordinates where x is r cosine theta. We need our limits written in the same coordinates as the integral. And then if we were asked for the volume of this region, well, we would just integrate the function 1. If we were asked for an integral of some other function to accumulate the values of that function over the region, we would put in the cylindrical form of that function right there and then crank this thing out.